I'd like to begin by thanking the organizers for putting together the 2025 version of Multiverse from Home, and also the invitation to speak. As the title of my talk indicates, I'll be talking about string theory and the multiverse. Let me start by giving some references. The connection between strings and the multiverse comes under the subject of string cosmology. There have been two recent reviews on the subject. They deal with this connection in detail, and also they build up on the subject of string cosmology from the basics and give an exhaustive list of references. So if you're interested, then these are places to start. Now, coming to the multiverse, the basic elements of the multiverse involve many universes, each having its own properties, fundamental constants, and cosmological histories. And then another important aspect is dynamical transitions between them, quantum tunneling, measures among these universes. And from the perspective of theory, when one thinks of the multiverse picture, a natural question to ask is, are there theories that admit the multiverse structure? And if so, how do these different universes arise in such a theory? And also, can we compute transition rates in the very early universe in such a theory? Does the theory have anything definite to say about the measure? And one important aspect in this is that the questions that one is dealing with involve both quantum mechanics and gravity. Therefore, one is really looking for a theory of quantum gravity. And therefore, I'll be talking about the multiverse in the context of string theory, which is a theory of quantum gravity. Now, let me come to the plan of my talk. I will start with a broad overview of the multitude of vacua of string theory. This is the subject of flux compactifications. I'll keep the discussion here fairly non-technical, given the broad audience. Then I'll talk about some recent progress in understanding flux compactifications. This will be slightly technical, intended more for the experts, if any of them are listening. And then I'll come to the second focus topic of this conferences, which is that of interesting future observations. And I'll talk about the upcoming area of high-frequency gravitational waves. So let me start with an introduction to string theory, and we'll go on to build on the picture of the multitude of vacua in string theory from there. So string theory is the theory describing the quantum dynamics and interactions of extended one-dimensional objects. They can be open or closed. It is a rich and highly constrained theoretical structure. In fact, various types of particles emerge at different excitations of strings. So in some sense, unifies the various particles. And also, gravity is naturally incorporated. So string theories just have gravity in them. We don't have to put gravity in as an extra ingredient. And it is widely believed that string theory has the promise to provide us with a quantum theory of gravity. This belief is based on its theoretical structure. And to give a few highlights here, it's known one of the famous problems in trying to quantize Einstein gravity is the problem of non-renormalizability. On the other hand, when one computes gravitational amplitudes involving string theory, one finds that those amplitudes are finite. So in some sense, string theory addresses the problem of non-renormalizability of perturbative gravity. The other area where there are interesting results is in the context of black holes. Black holes are believed to be fundamental objects in quantum gravity, and in various situations, people have been able to understand the microscopics of black holes using string theoretic tools. So we can explain the entropy of black holes. And at the same time, there are many open theoretical questions within string theory. But I think the successes give enough motivation to pursue string cosmology, that is, connect string theory to cosmology, or more generally to the real world. And in fact, it's very likely that asking these questions will also shed light on many of the open questions that remain. Now, string theory has a highly constrained structure. Firstly, there are no continuous free parameters. In QED, we are used to the fine structure constant being a free parameter, which we think is something that we pick. But in string theory, all fundamental constants are tied to vacuum expectation values of dynamical fields. Also, there's only one fundamental scale. This is the string scale, which is associated with mass of heavy excitations of strings. I will refer to this as ms. And even the number of space-time dimensions is fixed and is equal to 10. Now, in the weakly interacting regimes, there are 5 known string theories, but all 5 of these are related by symmetries. So the theory is best thought of as one theory. Now, we will focus on the weakly coupled limit of string theory that is known as type 2b. But because of these symmetries, the lessons that we will learn are supposed to be generic. Now, at energies close to the string scale or above, one directly accesses the physics of massive string states and their physics. These are many distinct features. Such features have not been observed in experiments so far. So it's most likely that experiments, actually the present day experiments, operate at energies which are much below the string scale. So what we should be really interested are the low energy effective actions which describe the physics of the light or massless excitations. Now, if we focus on type 2b string theory, the bosonic closed spring spectrum consists of a spin 2 particle corresponding to the graviton, the axiodilaton, which is a complex scalar, 2 antisymmetric 2-form potentials, and an antisymmetric 4-form potential. These form potentials are something that will play an important role in our future discussion. So let me go through what they are very quickly. So the form field potentials are generalizations of the Maxwell potential. And just as in Maxwell theory, we have associated field strengths. So in Maxwell theory, we have the gauge field potential A mu, and associated is a field strength F mu nu, which is antisymmetric in its indices. Similarly, if we have a 2-form potential, there's going to be a 3-form field strength, as in it has 3 indices, and it's obtained by suitable antisymmetrization. And in type 2b string theory, we have 2-form potentials giving us 2 3-form field strengths, which I will refer to as F and H. Now, coming to the gravitational sector, at low energies, the gravitational sector is described by the 10-dimensional Einstein Hilbert action. And to be consistent with observation, one considers solutions in which 6 of the extra dimensions are small and curled up along the lines of Kaluza line theory, and 4 are macroscopic and large, the ones that we observe. So the large ones are denoted by the indices mu and nu, and the internal ones, which are microscopic, I denote them as ym and yn. The simplest solutions are the ones in which GMN is Ricci flat. So the Einstein's equations in the internal dimensions are satisfied. Now, in such a background, the small fluctuations have a class of excitations that are associated with perturbations of the internal manifold. These are known as the moduli fields. So for example, if we have a solution of the following form, one can easily actually write a one parameter family of solutions, and this one parameter is essentially obtained by scaling the internal metric. And this is possible because scaling the internal metric preserves the Ricci flatness condition. The parameter lambda is directly related to the volume of the internal manifold. One can ask if this volume can depend on the position in the macroscopic dimensions. The answer is yes, because one also has a solution of the following form. Here you see that the internal manifold is multiplied by a factor which depends on the position in the macroscopic dimensions. And this form is a solution to the Einstein's equation if U of x satisfies the massless Klein-Gordon equations. Therefore, we have a massless field in 4 dimensions. This is called a modulus field. Now, massless moduli field pose a major challenge for phenomenology. These massless scalars would mediate long-range forces, and arising from the metric degrees of freedom, the forces would correspond to universal fifth forces of gravitational strength, and there's no evidence for such forces in nature. Another aspect of moduli is that their vacuum expectation set all the scales in 4-dimensional physics. For example, let's start with the 10-dimensional Einstein-Hilbert action that describes the gravitational sector in the 10-dimensional theory. If we integrate over the 6 internal dimensions, we see that the action takes the following form. And this shows that the higher dimensional Planck mass and the 4-dimensional Planck mass are related by the volume of the compactification. So in a situation where the moduli parameters are free, then we don't know what the volume is. So there's no predictability, as in we don't know what the 4-dimensional Planck mass would be. Now, so to summarize, when we have massless moduli, there are various phenomenological problems with forces and unfixed scales. And the solution is to consider more general solutions, and these involve non-zero vacuum expectation value of the form field strengths that I talked about. The physics here is very closely related to that of Dirac's magnetic monopole. Recall that for Dirac's magnetic monopole, consistency of quantum wave functions imply that the charge of the monopole, which I have denoted here by G, is actually quantized. Alternatively, one can say that the magnetic flux to the sphere encircling the manifold is quantized in appropriate units. Furthermore, when one considers electromagnetism in a compact space, it is consistent to have magnetic flux threading internal 2 cycles, that is the 2-dimensional submanifolds of the space, even in the absence of monopole. So one can just have magnetic flux threading 2-dimensional submanifolds, and And this can happen in the absence of monopoles. Again, consistency conditions require that the flux be appropriately quantized. Now, returning to type 2b string theory, the relevant internal six-dimensional compact manifolds are the so-called Calabi-Yau manifolds. These typically have a large number of three cycles, or three-dimensional submanifolds, which can be threaded by the three-form Friel's thread. So we have various three-dimensional submanifolds, which I denote by the index I or j. And through each of these cycles, one can have the three-form flux, and they have to be quantized just as in the magnetic flux in the case of monopoles. And so the solutions are characterized by these Zi's and these Zj's, which tell the amount of Dirac quanta of the fluxes that they have. So the solutions are characterized by integers. So in a situation where we have many solutions, the solutions are characterized by many integers, and therefore we have a multitude of solutions, but these are finite because of technical reasons that I'll get into later. So the fluxes also generate potentials for the moduli. Thus, the moduli become massive. There are no fifth forces. And the values that the moduli take at the minimum of the potentials, of course, depend on these integers because these integers determine the potentials. So essentially, the integers also determine all the properties of the solutions. So in summary, we have many solutions characterized by integers. The properties of the vacua depend on the integers, and the properties can vary almost continuously across these vacua due to a very large number of discrete choices. And in my opinion, this is fair to be called the string multiverse. And the solution space has all the ingredients to give us a fully realistic cosmology. There has been steady progress in this direction, getting a fully realistic cosmology out of it, but a model that's consistent with all observations so far is yet to be constructed. Now, work in this direction involves various technical and conceptual questions in string theory and detailed study, and a good fraction of the string community is actually working actively in this direction. Now, let me describe some technical progress in this direction. So this is really targeted at some of the, if there are any experts listening, and if you find it too technical, you can just skip this part of the slide and move on to the future observation parts. So now, as I said, integer data such as flux quanta and ranks of gauge group characterize string compactifications. And if we want to describe nature, we know that there are various hierarchies in nature, and a natural question to ask is what hierarchies can be generated from integers. Hierarchies from exponentials are well known, and I'll report on the possibility from polynomials. Now, the free-form flux F and H that thread the three cycles satisfy an imaginary self-dual condition when after the flux is complexified. The imaginary self-dual condition fixes the complex structure moduli, the dilaton, but there is no potential for the scalar moduli. There's a 4D effective field theory description given by the Gukov-Wapa-Witten superpotential, which is G wedge omega, omega being the holomorphic three form of the Calabi-Yau. And the flux chosen has to satisfy a tadpole condition, which essentially restricts the flux choices. So what are the challenges for getting interesting solutions? Well, the tadpole condition does not cut out a compact subspace of the flux vector space. Hence, one really doesn't know where to look for in the flux vector space. Also, the Calabi-Yau periods are only known as patches. Now, the strategy that was used in the present work was to work locally in the region of the moduli space, even within patches of the period expansion. One usually needs to do this because of the validity of the 4D effective field theory. For instance, one would work in the large complex structure limit, and also phenomenological considerations also drive us to particular regions in the moduli space. And the variables used are the ones motivated by special geometry of the underlying calabrium. Now, the IST condition in this language becomes a matrix relationship between the flux vectors, and the IST matrix turns out to be closely related to the gauge kinetic matrix of the parent n equals to 2 theory. So using this language, one can obtain bounds on the flux vectors in terms of local properties of the gauge kinetic matrix, so local in the moduli space. So here are some relations. We are trying to improve these bounds. But the moral is that with these bounds, one can sufficiently constrain the fluxes so that one lands in a particular region of the moduli space, and then look for interesting solutions in that region. To give one example, if one looks at the symmetric locus of the Calabi-Yau in P11169, this is a 2 moduli example in the large complex structure limit. The prepotential is a polynomial, implying the same for the superpotential. And for the following choices of fluxes, which I've written it, one finds that the vacuum expectation value of the vacua of the superpotential is of the order of 10 to the power of -5. Now, this implies a lowered scale of supersymmetry breaking purely from a polynomial superpotential, and also an interesting control parameter to look at solutions. So now, just to kind of recap on some aspects of this approach, the key advantage is that the present approach provides explicit flux quantum numbers for solutions of interest. So it opens up the avenue for various top-down studies. One has explicit access to features in the solutions such as mass hierarchies and voids in the moduli space. And it is also complementary to the statistical approach used to study these vacua back in early 2000s. Our results are in broad agreement, but with some interesting differences. So with that, I'll end my discussion of flux compactifications and move on to the subject of future observations. And there's a lot of interesting things here. The one that I'll focus on is high-frequency gravitational waves. The universal nature of gravity implies many sources for stochastic gravitational waves, such as cosmic springs, phase transitions, oscillons, but most of these are model dependent. But there's one that is guaranteed by the hot Big Bang model and is also UV sensitive. So how does this arise? Well, at temperatures below M Plancks, gravitons are not in thermal equilibrium with the cosmic plasma, but gravitons are constantly emitted due to fluctuations of the plasma tensor. For an observer today, these emissions sum up to give what is called the cosmic gravitational wave background, or the CGWB. Now, the theoretical prediction for this background from the standard model, or the BSM, has been computed. It's summarized by this equation. On the left-hand side, I have the contribution to the gravitational wave energy density today per log frequency band during one e-folding of the scale factor. And on the right-hand side, I have a source which depends on the property of the gauge theory, which is a property of the gauge theory at hand. Now, let me describe the features of this background as obtained from this equation by just qualitatively. Firstly, the peak. Where is the peak? Well, for most gravitons, the emission frequency is the frequency at the time of emission is the temperature of the plasma at the time of emission. And after emission, a graviton's frequency redshifts as 1 over AT. The plasma's temperature also does the same. Therefore, the peak frequency of the CGWB today is same as the peak frequency of the CMB, which is in the gigahertz band. Now, coming to the amplitude, well, the amplitude is actually proportional to the maximum temperature that the standard model plasma attains. And this is simply because there are more e-foldings of the scale factor further back. And this is what makes the quantity UV sensitive and interesting for high energy physics or quantum gravity. Now, today's experiment that operate, what are the prospects to see these backgrounds? Well, today's experiments operate very far off from the gigahertz band. But at the same time, there are many interesting developments in the high frequency range, and both in theory and experiments, and these are summarized in this living review that I urge you to look at if you're interested. To the extent that the first experiments in the area have already received support, so this is November 2024, the proposed sensitivities of these experiments are orders of magnitude below what is needed to observe the CGWB. So they're going to look at astrophysical phenomenon, but we should be optimistic as this is just the start of the era of high-frequency gravitational wave experiments. Now, finally, I would like to talk about the connection between gravitational waves, high-frequency gravitational waves, and strings. So what we did here is that we imagined that the early universe was at very high temperature, so that strings were in thermal equilibrium, and we essentially had a phase of very hot strings. And as the universe cooled, the massive strings would primarily decay to the standard model degrees of freedom, producing the standard model plasma, but a fraction of them would decay to gravitons. So the question we asked is, what gravitational wave background would this lead to? So one can compute this making use of the decay rates of massive string to gravitons, but let me describe the features. The firstly is that the frequency is also close to the CMB peak. But secondly, the amplitude is quite interesting. The amplitude is proportional to the string scale. So we really do see the UV sensitivity. And also it is large in the sense that it is orders of magnitude more than what the standard model or BSM would give if it went up to the same temperatures. Here is a comparative plot, and the solids is from what you get from the strings. The dashed is what one has from the standard model, and what one clearly sees is that the amplitude in the case of strings is higher, and also there are interesting differences in shapes, which is related to the structure of string amplitudes. So this, I think this calculation really emphasizes the importance of making the connections between high frequency gravitational waves and strings in the early universe. And that brings us to the conclusions. Well, we started with flux compactifications. I described the large number of solutions characterized by integers. We should think of this as the multiverse in string theory. Now, constructing fully realistic cosmological histories is one of the major open problems in string theory within this multiverse picture. There's steady progress in this direction. A big part of the community is working in this direction. And finally, I talked about high frequency gravitational waves and and how this can be a very interesting probe of string theory. Thank you.